So in the second part of the recording, uh, just a second, please. Yes, so in the second part of the recording, I will be meshing the model and then viewing the results, and I'll go through the procedure of the key outputs that we will be requiring in this case. Since the part is a fairly straightforward, simple, rod, so we don't need a very complicated meshing strategy. I'll just ensure that it is a high quality mesh that I'm generating, and in terms of the meshing parameters, I'll accept the default blended curvature based mesh, and I'll move it to the fine setting so that I've got a good resolution of my final mesh. So with this, once my mesh is complete, you can see the output here. So it is a reasonably refined mesh, and which will help us analyze our results quite closely. Now with this mesh, I will now go into the running of the study. So I'll basically now run the study, and this will help me calculate the final results. So immediately you can see output is there for von Mises stresses, but I'm not really interested in von Mises stresses. When you look into the model, the shape seems to be very strange. It is simply because of a very high deformation scale factor which is there. So if you put it on true scale, then you will not experience this. You can but you will not be directly using the von Mises stresses, but still it is good to have to see them later on for comparison purposes if you want to. So the outputs that I need and that I've asked you to calculate in the template is basically the tau xz and tau xy, which are basically the two shear stresses in the Cartesian coordinates. And this basically figure explains to you that in our formula for the theory, we are basically calculating this tau r theta, or this basically the value of the tau in a radial coordinate system, in a polar coordinate system, so which is always going to be tangential to this circular surface. But the finite element analysis is set up in xy and xz coordinate system. Basically, it is the Cartesian coordinate system. So we'll use this formula later on to convert from our xy and xz to the polar coordinate to the tau in our polar coordinate system, which we will then compare using the formula, and for which the calculations I've already shown. So secondly, we will be more interested in the stresses on the constrained edge, because on the free edge we will be measuring the deflection and the angle of twist, and on the constrained edge we will be measuring our stresses. Now to measure the deflections, we will basically output the values of uy and uz, and we'll use this formula to simply evaluate this angle, which is our angle of twist in this case. You can also use directly the value of the resultant displacement, and for comparison's sake, maybe I can show it to you later if you want, if you have the time. So let's go back and let's quickly then extract the required results. So I will output first of all the stresses, and then I will, or let me start by first outputting the displacements. Actually, it may be a good idea to, yes, plot the stresses first. And one thing that I wanted to plot even before starting my actual outputs that I'll need is the normal stress. The reason I'm doing this is that if my analysis has been set up correctly, then I should not have any significant normal stresses. Okay, so you can see here that my normal stresses are basically very, very low in this case, which indicates that there is no obvious problem with the model setup itself. So this is a quick check on the sanity of the model, but of course we will do more detailed validation later, and you can basically probe the value, and you can see that the stresses here are almost zero, so it is 0.051 megapascal. If you had not applied this constraint on the roller constraint here, you would see a slightly bigger number over here, which would indicate that there are some normal stresses because of flexure as well. So with that initial sanity check, we can now proceed to plotting the other stress plots. So let's start with the stress plot in the XY and XZ shears. So in our case, the XY shear is basically in the Y direction shear on this plane, which is our YZ plane. So on this frontal plane. Now, please make sure that you read the definition, and because you may have set up the model slightly differently, you may have set up the model with the long axis being y-axis. In those cases, then the meanings will change. So please make sure you output the correct components or keep consistent with the orientations that I'm using in the video. So with this, now I can simply output my results, and so this will help us plot the results. Okay, you can see that the stresses are fairly consistent. Immediately you can see and compare this number with the theoretical one that we are seeing, and you can see that the number is very close to this. But I'd want to basically I want you to understand that although you are seeing this maximum number here on a particular point to be very similar to what we will be calculating using our theoretical formula, the values of the stresses are not actually uniform all across this periphery, and this is a major difference from our hand calculations, because our hand calculations were giving a uniform value, and that was because of the fact that we were using a polar coordinate system there, and whereas here you'll have different values of xy and different values of yz. So immediately now, if I plot the value of the basically the other shear stress, which is xz, you'll see that the maximum for that will lie on a different point. Okay, so I can now simply plot this again, and as soon as I plot this, you can see that the location for the maximum and minimum have shifted. Basically, I can show you this more clearly probably by realigning our part. So let's say if you are viewing it like this, you can see here that in the xz axis, this is basically for the tau xz. These are the 2 points where the r theta stresses will be similar to your xz stresses. But then in the other case, basically these are the 2 points for the tau xy where the r theta stresses will be same. This is because in these points the xz stress will become 0 on these 2 points, so only the xy component is there, which is then equal to your r theta component. Whereas on these 2 points, when I was plotting xz, then on these 2 points the xy component basically becomes 0, and that can then be compared directly with the r theta coordinate system. Basically, this can be easily seen by looking at this formula. So when xz is 0, your r theta will simply be equal to xy, and when xy is 0, your r theta will be simply equal to xz, and that value can be directly compared. But we want to also be sure that the values are correct for the rest of the model, so we will actually export the data in Excel, and then we will compare those values as well with our theoretical formula. After this, we will plot the displacement plots as well, but let me first of all quickly just show you how to export the data in Excel, and then how to do the post-processing of the data in Excel as well. So there are several ways you can do this. I'll just go from the simplest way. So first of all, I have already actually created an Excel sheet, but I want to create a new one for you. So what I'll do is I will simply create another sheet in the same. So I'll insert a new sheet here. Okay. So on this sheet, I will basically copy my data. So I've set up a blank sheet so that you can see the whole procedure. So you can basically again go to the probe tool, and on the probe tool, instead of selecting a point, now you'll select the entire edge. Okay, and then when you say update, it will show you all the stress values on this edge. It also records the X, Y, and Z location for this, for each of these nodes, so all of those can be exported as well. You can plot it using the built-in plot tools of the SolidWorks as well, but because we want to do some post-processing on it as well, so we will be changing it. And you can see what I was referring to. So on the on these points, basically the maximum value of the you can see the xy is maximum at this parametric distance on the y-axis. So basically at the origin, so you can see that it is maximum on this top point. But right now I will just simply close this, and I will actually use, you can either use the save function to first export it into another Excel file from which you can then copy the data directly, or you can just simply drag your mouse, select all of these points, and then you can copy the data directly from here as well. So it's your choice the way you want to do it. I prefer basically exporting all the data. So I will basically export all the data, and I'll just put it in a temporary file. I will not really be saving that file separately, but I will just use the data in that file. So I'll then go to my folder where I have saved it. I'll open that. Okay, and it gives me the details. So I can either copy the whole data set if I want to, or I can copy part of the data sets. Okay, so I'll just move this over to my okay. So now next I will basically copy these two columns. Actually I will also copy the location column for now, but later on I will add more columns. Okay, so here I'm copying this. I just changed some of these tags so that later I remember which stress it is. So this is tau xy. Okay, and this is in megapascals. Right, so that's our tau xy, and I will basically move it here. So that later on I'll keep on adding more columns here for the same nodes. Right, so I've got my first set of data for the tau xy. Next I will go back to SolidWorks, say OK here, then I will highlight XZ, then again right click, probe, again select on the selected entities, select the edge that on which I'm trying to find the stress, update it. This time I will show you the second procedure where I'm directly going to copy this data. Okay, making sure that I've selected all the points, copy, and this time I will just simply just to remember that which data is this, I'll copy this line over. So this is not xy, this is basically xz. The advantage of copying it from the Excel is that you will get this information directly, so there is no chance of making a mistake related to that. You can see, so basically the stresses are in this column, which is the value column. So I'll copy this column over. You can see it's the same node numbers and the same distances, so make sure you're using this data for the same nodes. So I will now paste this data over here, and this is now my tau yz. Again, this is in megapascals. Okay, so after copying my stress data, next I will basically be outputting the displacements. And for the displacements, like I said, I can either use that resultant displacement directly, or I can calculate it using x and y. I want to show you the procedure for calculating it based on x and y, so I will be basically using that. So define displacement plot, and you can plot first of all the y stress displacements. Output it 4 places of decimal because it's going to be a small displacements. Okay, so this is my view of the displacement, but as I explained to you, for the displacement will be basically 0 on this edge, right? So we don't need it on this edge. You can actually check that, right? So you can see that the value is 0 on this edge. So that means we are not interested in the displacement on this edge, so it's on the complete edge at 0. So we are basically interested in displacement on the free edge, because here we have constrained the displacements, but in this edge we are free. This edge is free for rotation, so we'll capture the displacement on this edge. So I can, if you want, you can again change the view to see this face. And now select this particular edge. So I'll actually get rid of the other one, and I'll again select the first edge. Now yes, so I have to click update to make sure that the new values are recorded here, right? So this is now for the edge 2, and you can see the finite values of the displacement. I will again save this displacement data. I'll again open this Excel sheet. Oops, I think maybe it didn't get saved properly. Let me try again. Okay. Somehow I think probably the name is becoming too long for it, so it may be a restriction on my system, so I will just make the name shorter. Okay, so I'll just delete some of this so that it can save it with the correct extension. Yes, so it was basically error with the file permissions. Now when I open this, I can again copy this onto my own Excel sheet, or you can just do the post-processing in your sheet as well. It's up to you. So I'll put it here. Right. Basically, I'm after, you can see it's the node numbers in this case are different, the X and Y locations are different. So I will basically copy all of this data so that I'm not mixing the two data sets. So I'll copy this over here. Right, and this is basically my UI, right? And I really don't need the X and Y coordinates, but I'll still keep them just for sake of completeness. Okay, so basically these are the two columns of interest from the point of view of stress, and this is the column of interest for me from the point of view of y displacement. In the same way, I will also output the displacement uz. Okay, you can see again, just like the stress, the maximum and the minimum shifts. In this case, I did not define the max min, so you can see the location of the max and min reverses. Okay, so we'll use these numbers basically to calculate our resultant displacements. So in this particular case, we'll directly use again the probe feature, and again we are here on this edge, right? And then when we update, we are able to view the displacements along this edge. Again, I'm just shortening the name so that it can save it in the correct format. This time I'll just copy the value column because the rest of the data for the nodal points is same. So this is now uz, right? Okay, now my resultant displacement ur, as I indicated in the here, can be simply calculated as uy squared minus uz. Uz, looking at this, right? Sorry, this formula using the Pythagoras theorem basically. So we are just simply taking adding the two to find out the ur. The magnitude can be found from this. Of course, that for the direction you'll have to look into the vector addition itself, which will then give you the direction, right? So for the magnitude, we will be using so this is our ur. Okay, now I am noting that my radius of the shaft is 15 mm, right? So radius is basically 15 mm. I will calculate the angle of twist. Right, so I can calculate the angle of twist directly using tan inverse, so a tan of this ur divided by the radius r, but I will fix this reference because I want to calculate it for each based on each point. So this will be now my angle in radians, and then I will have it in degrees as well. Okay. Okay, angle in degrees will be simply obtained by multiplying this with 180 over pi, or you can use the built-in function of the degree in Excel. So this is 2.014. So immediately you can now compare that, the value of the tau xy and the angle of twist. So I will be looking at these numbers. So let's also calculate the value of the tau in r theta coordinate systems, or r phi coordinate systems. So basically this will be again square root of tau xy squared plus tau xz squared. So you can see, and now I'll just simply copy this formula over. So similarly I will copy these three formulas over as well, right? And you can see that pretty much the angle of twist is constant. This is expected, right? Maybe very small variations on certain locations, but because of some of the rounding error maybe, but otherwise we will have the same value of the angle of twist. So basically then these are our outputs that we want to compare. So the angle of twist in angle of twist, okay, and the value of tau r theta. So this is basically can be compared with the theory value. Now you can compare it literally for even a single location from the theory. Okay. So the value from the theory that we calculated, the angle of twist is this one. This is already explained in the previous video, how to calculate this number. And this is basically the theoretical value. Right? So this number is same throughout. Now if you want, you can calculate the percentage error as well, which I have asked later, by simply subtracting your simulation from the theory, and then calculating the percentage. But you can see here that the percentage error is really very, very small in this case, which is quite good to know. So let me actually just do that for percent error, or I will actually just call it as percent difference, because it's just slightly different assumptions that are causing the slight difference. So this minus this divided by the experimental, right? And you'll have to put a bracket here, otherwise Excel will give precedence to the division operation. Right, so this in the percentage. So I'll increase the decimals to highlight that. So this is around 0.86%. This is very, very small. So you can see that the error in this case is less than 1%. For the peak stresses, in the highest error is basically around 0.86. All the other places it's actually even less than that. Okay. Similarly, the percentage error in case of the angle of twist is also quite small. Okay. So basically this is the kind of output. Now once you have all of this output, you can then plot the required graphs and then input them here. So what I'm really after from you after this stage is you answer these questions and then compare the percentage errors and the percentage of displacement as well. And once you've plotted this, you should be able to show me the graphs of these as well. You should also take out a few snapshots of these stress states, for example, or the displacement, so that it's clear what you've done. Take a snip out of this and then include that in your report, so that your report becomes a self-contained document. And then in the last thing that I want you to do in this is to do the failure analysis and optimization. I'll let you do this yourself. So basically you'll be using one of the failure criteria. In this case you can use the shear stress criteria and then see whether you are able to, what is the factor of safety in this case that you obtain. Okay. You can use also compare it with the angle of twist. Clearly in my case the angle of twist is less than 10 degrees because it is only 2 degrees, and then here basically the desired factor of safety should be. So again here I've said both calculate, because the error is so small, so you can just simply use one of the two values to basically calculate this failure, and the answers will be same. So you can just comment on this that the answers will be very similar because the error is the difference is very small in both the theory and the FEA. So you can then apply the failure criteria. So once you have done this, then in the next part I'm asking you, so in my case, for example, the shear strength of the material, I can just show you quickly. So you've got here, basically what you'll need to do is you'll need to calculate your principal stresses. You can directly either calculate that, principal 1 and principal 2, or you can just use the formulas for this and then calculate principal. That's why I said to you, you can choose your method. But what I'm trying to say here is that you will need to know the strength of these materials as well, which you can directly see by going into the material option. So if you go into the material option, you'll be able to read both the tensile strength, the yield strength, right, and then basically you don't have the shear strength, which is basically what you need to compare it against. So this is why it is important to then decide which criteria you will be using. Okay, so and this is then that discussion comes into play, which I have made in the lecture part about the different estimates for steels as well as for brittle materials. So please have a look at those slide notes. In particular, you can use for ductile metals, you can use the estimate of the shear strength being half of the tensile yield strength, but that will only be applicable if the material that has been given to you is a very ductile metal. Otherwise, use the estimates that are given that I have discussed in the slide. So that's it from my side for this video. I hope you will be able to complete the rest of the steps in the report, because once you have calculated this, then the next step is that I want you to suggest some design changes that will allow you to reduce the mass by around 25%, and then validate your changes and then upload your results. Thank you very much.